till now I talked about the word sequence, okay, and if you recall, the word sequence problem can be dealt in two ways. So, this is one way of dealing with it, okay, and the other way is the word sequence itself, okay. So, we are going to talk about this kind of an approach, and we are going to call specifically something called n-gram. We are going to introduce something called n-gram, okay. What is an n-gram? The n-gram is nothing but given, you know, some history, but I am not going to look at the entire history. I am going to restrict. So, if you look at the Markovian process also, right. So, when we said that the next day weather depended only on the previous day weather condition, right. So, first order Markovian process. Similar kind of concept happens here also. What we are saying is the prediction of the next word depends only on the previous word. If I make such an assumption, okay. So, next word depends on the previous word. So, these two words are there. So, then we call that as a bigram, okay. So, I am only going to use to predict the next word only the previous word, and I find out how often given this first word the second word occurred, okay. So, this is like historical data on weather. Here I am looking at historical or the entire text data in the entire universe, right. I can take all the text data that I can scrape from the web and then try to find out this probability, okay. The probability of a word in itself, how do you find out? It's very simple. I take all the words in the world. Let's say I found out that there are 1 million such words, okay. Then I found out how many of them are unique. Let's say only 50 are unique, okay. I'm just giving an example, right. So, there are only 50 words that are unique. So, now what is the probability of each word, right? How do I find out among this 1 million, each one of those unique words, how often did they occur, right? So, let's say the first word occurred 10,533, right? So, the probability of the first of the word, right, there are only 50 unique words or something, probability of word 1 is 10,553 by 1 million. Like that I do for all the 50 words, right. This is basically unigram, right. So, in a language there are some words that are highly probable, some words that are very rare, right. So, the unigram tells the probability of each word in the which are the least probable words and which are the most frequently occurring words, like and, the, is. All of these are commonly occurring words in English language, right. But words like flaxy, poxy, nihilipilification, right, that's one supposedly the longest word or something, right, that is very, very rare. You probably would have never heard of this word, right. So, this word, right. So, so we normally all of them have long, what's called long tails. There are many, many words that occur very infrequently, okay, only few words. So, if you look in our vocabulary itself, everyday conversation, you will see that we don't use more than some 2000, 3000 words, right, which always keep occurring, right. All the other words, the vocabulary might be even a million, right, but all the other words occur very rarely, okay. So, there are only 2,500, 3,000 words that normally we tend to use quite often, okay. And among these also, like the and, the, and all of these are very, very frequently occurring in English, okay. So, I talked about unigram. Unigram means the probability of each word in that language, okay. So, there are many words that very infrequent, have very, very low probabilities. Bigram is given one word, what is the probability of the next word occurring, right. So, that is the bigram. So, this is clearly illustrated here. So, if I look at the sequence of words, this is a sentence. So, there are 4 words. This is a sentence, right. Now, what is a unigram? It is a probability of the word this, the probability of the word is, the probability of the word a, and the probability of the word sentence, right. How probable these are. So, these are called unigram models, okay. Now, bigram, I told you one word, how dependent, what's the probability of the next word occurring, right. So, now what happens in bigram, it is 2 words at a time. So, this is, so given the word this, how often does the word is occur. So, together this is going to be given this, how often does is occur, that becomes a bigram, or given is and a. Now, is and a form two consecutive words. Given the word is, how often does a occur? Then a sentence. How often does the word sentence occur after the word a? Okay. So, these are called bigram, right. So, remember we are doing this conditional kind of things. If you recall, we were talking about, sorry, I keep going back, but I am trying to do these kind of things. Okay. So, this kind of thing, I am looking at the conditional kind of things. Okay. So, here if it does not depend, so this probability of x1 by itself, this is going to be basically just the unigram, okay, for all words if I am looking at, okay, x first word, second word. If I am looking at this, this is a bigram, right, the probability of a word x2 given word x1, right. So, that is basically bigram. So, this is going to be what, this is using t minus 1. So, if you see uni, then bi, so there are two words. Uni means one word probability, bi means two word probability. So, this will be what, capital T words are there, the t minus 1 dependence and then that word itself. Bi, it depends on 2, uni depends on 1, capital T. So, this is a T gram, capital T gram model. Okay. So, normally we use the term n gram. So, a probability of the nth word given the previous n minus 1 words instead of t minus 1, normally we use t n, right, for language models. That is historically the way we always prefer to call it. So, this is basically n gram model, right. So, that is the term that is commonly used. Similarly, I can have a trigram model. Tri means 3 words, but actually I am asking the prediction of the third word given the previous 2 words. So, I need 3 words, that is why it is trigram, but the third word given the previous 2 words. Okay. So, if I look at 3 words in consecutive words, this is a, the probability of a given this is, that is a trigram, okay, or 3 gram. Okay. Bigram means 2 gram. 1 gram means unigram. So, after the 3 trigram, we have 4 gram, 5 gram, 6 gram, 7 gram, like that we go. But okay. And similarly, this is one thing, is a sentence, probability of sentence given the words is a, that forms a trigram language model. Okay. So, this is basically what is this idea. Now, how do we compute these probabilities? Okay. So, it is exactly like the weather. I told you historically we are going to look at data and see how often sunny occurred. After sunny, if I am looking at probability of cloudy given sunny, I look at how often given sunny has occurred, the next day was cloudy. So, I count these two, right. So, I will show you that example here. So, just to summarize what we have taught, n-gram language model means the tth word, whatever word depends only on the previous n minus 1. So, these if I am in the tth word in a long paragraph or whatever it is, right, it is only going to depend on the previous n minus 1. Okay. So, in an n-gram language model, the prediction of the n of this word will only depend on the previous n minus 1 words. Here we are talking about words or events and so on. This is very different from something which long back in the beginning of the course I talked about, something called linear prediction, where I am depending on the previous samples to predict the pth sample, right, previous p samples, right. That is where we are actually finding the value. Here it is an event or a word or something. Okay. So, these are different. I mean, here we are talking about events, states, things like that. Okay. And how do we do this? This one again, the same idea is nothing but, so this is conditional, is nothing but the joint divided by the the condition, right? So, probability of xt minus 1. So, all xt minus 1 all the way, the joint has to come on the numerator. So, here it is conditional, xt given xt minus 1 up to the n words before, that is equal to the joint of xt minus 1 until the n minus 1 word, divided by the condition part of it, which is the joint of the probability of xt minus 1 up to t minus n plus 1, right. So, these two are the probabilities I have to find, but we do the usual count way of probabilities, right. So, we take, I told you, we are going to take enormous amount of text, right, find out how often this sequence of t words, right, n words occur, sorry, this n minus 1 plus this word. So, the together the n words, again this is a sequence of n minus 1 because it starts minus 1 and goes. So, basically this is always going to have a larger count, right. So, number of times sunny occurred words, that will be like the denominator, like a bigram if you are talking about, and the number of times sunny and cloudy, sunny followed by cloudy. So, sunny can be followed by cloudy or sunny again or rainy. So, there are three choices, right. So, the number of times cloudy is going to be a subset, right. So, fewer times. So, the numerator is saying xt minus 1 is the number of times a certain event occurs. Out of it, the following word is xt is going to be, can be any one of those 1,000,000 or 10,000 words. So, I am choosing a particular word. So, the numerator will always be a smaller quantity, right. The count will always be smaller. So, this will actually always be a number between, so all of them are counts. So, they are non-negative numbers, right. In fact, most of the time here we are talking about integers. So, we have to divide to get the probabilistic kind of thing, we have to divide by the total number of occurrences and so on, right. But you know, you can get the feel, right. So, this is all, the numerator is smaller than the denominator. So, it is always going to be less than 1 for sure, and both of them are non-negative. So, they are always going to be greater than 0, right. Okay. So, now that is the basic idea in language modeling. So, this is where I am saying Google and all of these people, they have counted, or they have kept this huge, gone through a lot of text data over the many years and have figured out very well, how often a sequence of words occur and so on. Okay. So, this is something that is a repeat of whatever I did, and of course, when I told you this multiplication, if I am looking at the joint probability, it is a multiplication of the unigram multiplied by the bigram multiplied by the trigram and so on, right. So, that though each one of them will be done by the count method. Okay. But there are some issues that we have to worry about, and I will explain to that a little bit, right. And so, here we will take a very good example of what we are trying to do. So, suppose we are talking about a 4-gram language model. Okay. What does 4-gram means? So, that means there are 4 words, but I am predicting the 4th word based on the previous 3 words. That is what a 4-gram model will mean. Okay. So, if the sentence is, as the proctor started the clock, the student opened there, and I will give a blank, fill in the blank. Okay. So, that blank is what word, what W, what word are you going to put there. Now, because I am only talking about a 4-gram model, so W is the word that I want to predict. It will only depend on the previous 3 words. So, there, opened and student, these are the previous 3 words that you are going to look at. Okay. So, in some sense, we are now showing you the deficiencies of the n-gram model, and that is where a powerful neural network based model called the recurrent neural network RNN based language model, which was developed by one of our colleagues. I mean, we collaborate a lot with the Brno group. Honza is the main professor there. His student Mikhailov, who is now almost leading the Facebook efforts, right, is the one who came up with this idea of the RNN language model. So, we will come to that a little later, but we are going to actually start showing you some of the deficiencies of the n-gram model, which was very powerful until the recurrent neural networks came about 7, 8, 9 years back. Okay. So, because of the n-gram being only 3-gram, and the problem is the counts do not happen very often. Remember, I say only 3 or 4,000 words keep occurring again and again in a particular language, this problem is going to come. Okay, we will show that in something. So, now if I am talking about a 4-gram language model, what do I need? I need the probability of the word W, which I don't know, there could be any word in that vocabulary, given that students opened there, that I have seen, okay. But I am now trying to predict this word and find out that word which has the highest probability, right. So, I am going to count with all possible W students opened there, I am going to look at all possible words that followed in my, when I was training, and followed and the number of times students opened there, okay. And let us say that these two possible occurrences happen. So, in my training corpus, right, when I looked at a huge amount of text data, I found out students opened their book, okay, occurred 400 times, okay. First of all, student opened there, the sequence of these three words occurred 1000 times, let us say. Then out of those 1000 times, students opened there 1000 times, the next word, right, among these 1000 times, next word book occurred 400 times. So, the sequence opened their book happened 400 times divided by sequence opened there occurred 1000 times. So, now the probability of book given students opened there is 0.4, right. Similarly, I found that exams, students opened their exams occurred 100 times, okay. So, now what will be the count type? So, first I take the numerator will be students opened their exams, which is 100 times, divided by only students opened there, which is 1000 times, and this is 0.1, okay. But actually the problem is that the n-gram is not very good at capturing, because we are only looking 3 words in context, or 4 words in context, and the reason why we can only look at this, even 5 word and 6 word become very difficult, I will come to it, because we are using the idea of count method, okay. So, therefore, if you look at it here, would you have said book, remember, occurred a lot more time and then exam was smaller, right. But how did you say, if you had looked at this sentence, what would you have predicted? You as a human being would have said exam is more likely here than book, okay. Why? Because of this proctor, right, the proctor word, or start of the clock, all of these give you a sense that that student is sitting in an exam hall or something, correct. There is a question of time and hall, I mean starting the clock and proctor, so all this gives you in your mental image a picture of somebody monitoring you, invigilating you, your clock is running, right. So, you as a human being understood that you have to focus on these words also. So, there is some information that was very important, but when I used the program, it never had this context to worry about. It only looked at these words because it's only looking at previous 3 words. I don't care what happened before. That's where the RNN language model is going to help you. It look much more into the past to help you determine more correctly the correct answer, okay. So, if you had seen the word proctor, and as human beings we are super brains, right, machine is only looking at 3 words, but you could look much behind, and therefore you could sort of predict that it should have been probably exams is much more sensible than book, okay. So, this we are going to see that the language model built by RNNs are going to be very good at such kind of jobs, okay. Now, there are many problems of the language model, right. One of them, as I said, is that we can only have 3 or 4 words in the history, because the simple reason is many of these never occur in the data, okay. Even if when I say infinite, I don't have infinite. Now, I am I am human, right? So, probably even Google, right? It can do only so much. And if I am sitting in a lab as an academician, or a researcher, maybe I have even more limited resources, right? So, I might be able to capture some material from 10 books, maybe 20 books, or last 3 months worth of scraping of the web data, right? Maybe something like that, some finite time, right. And there are lots of things where the cases where many of the sequence of words we will never get to see. Not that they will not occur, okay, they will occur, but it's just that you don't get to see them. They are all rare events. They occur very infrequently, right? So since we know that, in the data, in the training data it never occurred, but we know in life it will happen, right? So this is where we talk about the long tails of many of these languages. So how do we cannot put zero probability, then we will never predict that the students, whatever it is, that exam, if it never occurred, you will never predict that word, okay, and you will never get that, okay. So what we do is we take all possible words and we add a little bit of a small value, right? This is called smoothing. So we remember the total probability should add up to 1. So where there are a lot of masses, right, where the high probability, we take a small delta out of those high probabilities and put it into small probabilities wherever it has gone to 0. So that if you put it 0, because you are using count, the probability will go to 0. We will say that will never occur, okay. We don't want that. We are saying it will occur, but very, very rarely, which is the more realistic scenario, right? So we add all, take a little bit piece by piece from there and redistribute it to all these rare things. That is called smoothing, okay. So that is one way we compensate or get over the problem. Then there is another thing. Sometimes if you are looking at large vocabulary, right, long language models, n gram, 5 gram, 6 gram, then the probability of sequence of 5 words occurring, because of joint probability, right, it's always multiplication, right. Joint probability means it's going to get probability of unigram, right, is higher, right. Then multiplying 2 words, then both the words have to occur, this word and that word. Obviously this word itself has a number less than 1, right, because it's probability. Then I multiply 2 numbers less than 1, it will become even more smaller, right. So if I have 0.9 and 0.8, right, if I multiply the 2, it becomes 0.72, right, which is lesser than these two, right. So they are going to be even more rarer and rarer and rarer, right, and therefore we have to back off. So if I am not able to find a 5 gram, I look at least what is happening in the 4 gram case, right, which is at least, if 5 gram had gone to 0, it becomes so small that my computer, right, it falls below the whatever my computer can represent, then I back off and say, okay, at least 4 gram is something happening, okay. So that is called back off, right, I'm backing off, okay, I can't do that, let me go to a slightly bigger problem, right. So this is called backing off, okay, and the other one is called smoothing, okay, and so many issues are there. So I'm just going to give you an idea of what is language model. We'll see that the RNN language models are quickly taken over, and then how do you evaluate this language model? Again, there are many things, but you will come across something called perplexity, and basically the idea is that if you have built a very good language model, it will have low perplexity, okay. So this term perplexity is what it means, that is a very good low perplexity model or a very good language model will predict with a very high degree of accuracy the following word given, right, sequence of words, predicting the correct word, the next word will be very high in a low perplexity model. And what low perplexity means? Low perplexity means that basically these occur with a high probability, right. That means you have seen them, right, you have confidence in them. Yesterday I went to the cinema, hello, how are you, it's how are you, okay. So already the spelling, but the dog was wagging its tail. These are commonly occurring. So if I say the dog was wagging its, then you'll know it has to be tail, right. So this is a low perplexity model, means it will model very well, okay. Whereas when you have high perplexity, it will not predict the next word properly, okay, and that can happen because and so therefore you can can you, does it, for wall or driving, some random sequence of words. Now this language model does not it has not seen more commonly occurring sentences, and so in this kind of language modeling, right, so when you are looking at 3 gram, 2 gram or 4 gram, right, what happens is it's not looking at the context. So when I combine these two, right, the two, even though the sequence of 3 words might look good, but when I combine to form a proper sentence, they might not form a proper a commonly occurring mixed sentence, okay. And so that then you start getting high perplexity, which means the probability of these sentences occurring are very low, okay. So therefore term perplexity, and actually there is a mathematical way of sort of capturing this. Basically what it says is, whenever you have high probability sequence of words that are highly probable, right? That means you've seen them often, you have very good confidence and so on, then the perplexity is inversely proportional. That's what it's trying to sort of tell you. Okay. So I think that is all I want to say. I want to finish this portion about language models, and tomorrow or the next class I will start with the idea of neural networks, right? And we will come back to the sequence of words, right? And from the sequence of words, we talk about the RNN language model, how it is capturing this long history. From that idea of the language models and the sequence, we will slowly start seeing, something called word to vec. Then from word to vec came this in the NLP kind of framework. Something called BERT came up. Okay, something called GPT came up, which is really powerful, right? These are all language models actually. GPT is definitely a language model. BERT is more a context dependent representation. It's difficult you can interpret, but normally GPT is almost a correct, is exactly the language model that you're talking about, which you may have heard: GPT-1, GPT-2, GPT-3, and so on. Okay. We will talk about these things as we go about sequence modeling and so on in the coming classes. Okay. So I will stop here. Thank you.